So before we start, do you have any questions? Whatever we have discussed till last class? Okay, so if not, then let's start. So in the last class, we discussed about PN junction, right? So we discussed the basic uh, fabrication of PN junction, and we also discussed about the depletion region. So the moment you connect P to N, so the holes flow from P to N and electrons flow from N to P. But in the equilibrium conditions, so there is an electric field which prevents the flow of holes from P side to N side and electrons from N side to P side. And so uh, so in the equilibrium conditions, right, so there is no current flow. So at this point we have a depletion region on the P side, I have a depletion region on the N side. So the depletion region in the P side has negatively charged acceptor ions, and the depletion region on the N side has positively charged donor ions, right? So also so let's say uh, so minus xp is the extreme edge, right? So uh, okay, so this is my x direction, right? So if I'm going from left hand side to right hand side, so the first edge of the depletion region is minus xp, your junction is at 0, and the right edge of your depletion region is xn. So the depletion width in the p side is xp and depletion width in the n side is xn, right? And the total depletion width wd is nothing but xp plus xn. Okay, and other region, so we have a neutral region. So in the left hand side and right hand side I have a neutral region. Wherever there is no depletion region, so that is the neutral part, right? So what do you mean by neutral part? So the total charge, right, if you sum the charges in that region, that is 0, right? So just to mention here, so when I'm talking about total charge, so total charge is P, so definitely Q times P minus N, or you could write also in this way, P plus the donor ions minus N and minus acceptor ions, right? So this is 0, right? So if this condition is satisfied, that means total charge is 0, that means this region is neutral. Neutral means there is no electric field. If the total charge is 0, there is no electric field, right? So please keep it in mind. Right? So the electric field is 0. But if you look at the depletion areas, right, like in the P side and N side, so there is a net charge, right? Okay. So also, uh, let's say the field. So basically, the moment we have charge, there will be field. Let's say the field at this point is E1 here at the left edge, at the point 1 here at the left edge of the depletion region, and that junction, let's say the field is E2, and the right edge, this is E3, right? Uh, right. So you could write the Gauss law, right? So so basically what I'm interested in, how the electric field varies if I go from left to right. So uh, uh, right, so in the left hand side, so if I go from this contact here, right, so this is my metal contact, right? So metal contact to the edge of the depletion region, there is no electric field because there is no charge, right? So the moment I reached this edge, right, so so the left hand side depletion edge, right? So I'll have, means before that I do not have electric field, and at that point, let's say the electric field is E1. So the Gauss law means we also discussed. So let's say total charge in the QP, right? QP is the charge in the region between minus XP to 0, right? Minus XP to 0. So total charge is minus Q times Na into XP into junction area, right? And similarly Qn, so this is between minus xp x0 0 x xn, right? So your qp is minus qna, total charge, right? Na is the volume charge density per centimeter cube, right? So total charge is minus q times na into xp into aj, and similarly qn is q times nd into xn into aj. Then if I solve the Gauss law, so if the E2 minus E1 is the electric field at the the edges of your XP, right? So E2 minus E1 is 1 by epsilon minus XP to 0 rho x dx, right? But in the E1 equal to 0, because at this boundary, because this is the end of the neutral region, so at this boundary my field is 0, right? So if I do that, I could write E2, I could write E2 is 1 by epsilon QP by AJ, and I could also calculate, right? E2 is the electric field is nothing but minus 1 by epsilon QNAXP, right? So field is negative, that means the field is in the opposite direction, right? So your x is from left to right. So since this field is coming out to be negative, that means your field is from right to left, right? So here the field is right to left, right? Because of the negative sign. Similarly, you could do this math also. You could solve the Gauss law, and you will get that your E2, your the electric field, uh, because you see, again, if you write the Gauss law, right, uh, means the both sides of xn, right, between 0 and xn. So you will see that E3 minus E2 is 1 by epsilon integral 0 to xn qn by ajxn dx, right? So if you solve that, then your E2, because E3 is 0, because you see this is also the sorry, so this is also the edge of the neutral region, right? So your electric field has to go to 0, right? This is the boundary, right? So so your E2 E3 will be 0, so E2 will be also qnd xn by epsilon, that is also negative sign. So the field is from right to left, right? So then because this, when you take E times the epsilon times electric field, that will give you the electric flux, right? So epsilon times electric field E2 is the electric flux entering the xn region, right? The depletion region in the n side, right? And so you could, so the flux entering at this boundary, right? If you look at this boundary here, this boundary here, right, your flux, electric flux should be continuous. So epsilon times E2 will be epsilon times, right? So the flux coming from the XP region is QNA times XP. The flux entering the XN region is QND times XN. So those two flux will be equal. So we have this NAXP equal to NDXN, right? So here the XP is the uh, depletion region in the P side, right? So region P side, and this is N side, and your total depletion width is nothing but will be xn plus xp. Okay, all right. So before we go to the next stage, let me tell you something about one approximation that we'll use. That's called depletion approximation, right? So how many of you heard about depletion approximation? I mean, many of you might have heard, right? All of you might have heard about depletion approximation. Bhavesh? Sarda? So what is depletion approximation?
So, sir, basically the voltage drop which happens in a diode is only across the depletion region.
That is depletion approximation.
And like there are
No, what is depletion
no,
approximation? I'm not getting my point. What is that approximation? Why you are taking this approximation? So this is called approximation, right? Why it is called approximation? It's not a exact uh, thing,
okay.
right? This is approximation.
like there are no charges in depletion region, like no free carriers in depletion region.
Why is that a approximation?
Mm.
Okay, Shruti.
Sir, I don't know about this.
Okay, Nishant.
नहीं सर नहीं मालूम.
Okay, anybody who could answer what is depletion approximation? Swati.
Sir, it's like there are no charges, but they recombine when the holes from one side and electrons from one side recombine. It may
No,
be like
recombine. That is not a depletion approximation, right?
Sir,
See, yeah,
the-
Bhavesh,
the depletion rate is 0, means consider that it is 0, maybe a
no,
approximation.
depletion width cannot be 0, right? Depletion
Yes
width.
sir, it is not 0, but it is small, so can.
Okay, okay. So let me let me tell you what is depletion approximation, right? So you have some ideas, but not very clear idea, right? Okay. So if you look at, so this is my junction, right? This is my junction, which is x equal to 0 is my junction, and I'm telling that okay, this is my minus xp point. This is the edge of the depletion region in the p side, and this is the edge of the depletion region in the n side. And I have okay, I have negatively charged acceptor ions here, and positively charged donor ions other side, right? And I have, so as we saw in the uh, last page, so you have a electric field in this direction, right? Electric field in the negative direction. So electric field is always from n to p, right? Okay. So if you look at p side, right? So let's say p side, your doping is Na, and n side your doping is Nd. So I have let's say the number of electrons in Pn will be Ni square by Na, and number of holes in P is Na, right? This part you know. So in the similarly, number of electrons will be Nd here, number of holes will be Ni square by Nd, right? So if you go from if you go from right hand side towards the left hand side, and just look at the whole concentration, right? If you look at the whole concentration, let's say Na equal to 10 to 17, or let's say 10 to 17, and so this will be 10 to the power 3, and this is 10 to 17, and this is 10 to 17 and 10 to 3, right? Assuming both are 10 to 17, right? Okay, so if you go from left to right, you will see that the whole concentration is 10 to 17, right? Right. So, and in the n side, it is 10 to 3, right? So it was coming from 10 to 7 to 10 to, 10 to 17 to 10 to 3, right? And that transition from 10 to 17 to 10 to 3 is happening in this region, right? In this region here, right? Right. So if you see, let's say this is my region, depletion region, right? So left hand side of the depletion region, I have 10 to 17 holes. Right hand side of the depletion region, I have 10 to 3 holes, right? But these holes, I mean, concentration of holes cannot be discontinuous, right? So there's a continuous, right? So basically your hole is you're decreasing from 10 to 17 to 10 to 3 somewhere in the depletion region, and that transition is happening somewhere in the depletion region, right? But if you similarly, if you go from right to left, or left to right, so you have 10 to 3 electrons here, right? 10 to 3 electrons, and you have 10 to 17 electrons, right? So your electron concentration is also increasing from 10 to 3 to 10 to 17. So when I'm talking about the electron concentration, whole concentration, this is 10 to the power 14 times. There is a change of 10 to the power 14 times concentration change, right? Across the depletion region, right? And if you look at the depletion width, right? So this is maximum few hundreds of nanometer, right? What will be the width of the depletion region? Right, the width of the depletion region will be hundreds of nanometer, right? Right, right. So if you see in 100 nanometer, there is a 10 to the power 14x change in electron hole concentration, right? So if you look at, so you could assume that your 10 to the power 14, right? If you see the 10 to the power 14, right? Uh, right. So 10 to the power 14 is changing in 100 nanometer, right? So that means this change is happening very fast, right? Right. So if since this 10 to the 14 transition is happening in very few hundreds of nanometer, even less than hundreds of nanometer, so you could safely assume that the carrier concentration, right, hole and electron concentration is very less in this region, right? Right. So hole and concentration in the depletion region is not zero, right? As I told you, there is a continuous, because hole concentration changing from 10 to 17 to 10 to 3. That means there are some number of holes in the depletion region and there are some number of electrons in the depletion region, right? So concentration of electrons holes in the depletion region is not zero, but since they are rapidly changing in the depletion region, you could safely assume that the concentration is zero, and that approximation is called depletion approximation, right? Without this approximation, this approximation is first time given by Shockley while he is deriving electron hole concentration in the semiconductor, right? So without this approximation, you cannot really go ahead and do the calculation, because you cannot solve Poisson's equation, right? Right. So this approximation is a very fundamental approximation, and that is
Sir,
very well valid also, right? Huh.
sir, can you just repeat what you have taught in the last 2 minutes? I got
So what
disconnected.
I'm telling is the electron hole. See, so we have if you look at the depletion region, right hand side of the depletion region, left hand side of the depletion region, I have 10 to 17 holes. Right hand side, I have 10 to 3 holes, right? So the whole concentration in depletion region is somewhere between 10 to 17 and 10 to 3, right? Because the transition is happening in the depletion region, right? But that transition is happening in a very small x, right? In a hundreds of nanometer, right? So that means the concentration of 10 to 14, the change in concentration of 10 to 14 is happening in hundreds of nanometer, right? So you could safely assume that since the whole concentration is rapidly reducing from 10 to 70 to 10 to 3, you could assume that, okay, I could take assumption that I don't have any holes in the depletion region, right? So that approximation is depletion approximation, right? Right. So this is an approximation, and without, this is a very fundamental approximation, right? And without this approximation, you cannot really solve the electrostatics of any device, right? Right. Uh, Okay, so if I what I'm telling here is, if you look at the constant, let's say this is my x direction here. This is my x direction, and if I want to, this is my depletion region, right? Depletion region. So actually, what happens is, so I have my hole and 10 to 17, and let's say 10 to 3 here. This is 10 to 17, 10 to 3, right? So 10 to the 14 change is happening somewhere here, right? But since this distance is very less, right? Means you could see hundreds of nanometer, right? So your 10 to the 14 x change of holes in these hundreds of nanometer. So you could safely assume that you have a depletion approximation just tells you this, right? So I can assume this curve was this curve, right? Sorry, this curve. So red curve on the this curve, right? So I'm just approximating the red curve by uh, um, by by this purple one, right? So this is the depletion approximation, right? Similarly, the electron concentration, I could also put the electron concentration. So electron concentration, if I do the depletion approximation, this will look like this, right? But actually it was happening like this, right? But this is exponential reduction, and this distance is very small, right? So assume I am talking about hundreds of nanometer, this area, right? Only hundreds of nanometer, right? So this drop is very rapid, right? And you could safely assume this curve has this curve, right? And this is the, and this graphically represents the depletion approximation, Okay, so is it clear? Is it okay, Shruti?
Yeah, yes.
Okay, all right. So yeah, so this is depletion approximation. So by taking the depletion approximation, okay, we are telling that okay, there are no electrons holes. Now we could solve the Poisson's equation to get the electrostatics, right? So in the next few slides, I'll just derive the electric field distribution, electric field and the potential distribution from right hand side to left hand side to right hand side. But since many of you have already gone through these derivations in your electronic devices course, might be right. So I'll just go through it quickly. Um, so here, right. So I derived this right in XP, and I have taken this depletion approximation, right. I've taken this depletion approximation. Right. So now just to solve, I have to I have to write Poisson's equations, or I could even solve by Gauss law, right? So this is the Gauss law: d by dx equal to rho x by epsilon. So I have four regions here. So I have two neutral regions, and I have a region with negatively charged acceptor ions, and I have a region with positively charged donor ion sites. So the neutral region, your electric field is zero. If the electric field is zero, there is no potential drop. So I'll not talk about the neutral region. But between minus xp and 0, so I have a region where I have negatively charged acceptor ions. So if I solve the Gauss law in this region, so d by dx will be minus q na times epsilon, right? And q na is the volume charge density, right? This is per centimeter cube, right? Minus q na divided by epsilon. So then if you solve this, your ex, the electric field, is nothing but minus q na by epsilon times x plus a constant c1. If you, this is a partial derivative, so you have to solve that. So at the edge of the depletion region, at minus xp equal to 0. So if you put, then you will get this constant, right? Your c1 is minus q na epsilon by xp into xp, and you could get your electric field. How does it change with x, right? But keep in mind, this is only between minus xp and 0, right? This is between minus xp 0, right? So this is my electric field. How does it vary with x between minus xp and 0? So electric field, I could also mention the potential minus dv by dx, right? So minus dv by dx will be this one. So dv by dx will be qna by epsilon times x plus xp. So again, if I take the integral, I'll have this, right? So qna by epsilon x square by 2 plus x times xp plus c2, right? So the voltage, so basically if you look here, I'm not applying any voltage across the contacts, right? So the voltage here is 0. So there is no voltage drop in the neutral region. So at this edge, the voltage will also be 0, right? So I have taken this assumption, I mean, not assumption, so this boundary condition, a voltage at minus xp, a potential at minus xp equal to 0. If I do that, then I'll find the constant, right? C2, right? So if I do put C2, then my Vx will be Qna divided by 2 epsilon x time x plus xp whole square, right? So here you see your electric field is linearly varying between xp and 0, but your potential is quadratically varying, right? That's the reason when you draw the band diagram, I told you in the last class, uh, I cannot really connect the conduction band of the n side and conduction band of the p side by a straight line, right? So I have to use a quadratic function, right? Okay, right? So if I summarize this part here, um, uh, so so your electric field uh, is linearly varying between my xp and 0. So this is minus qna divided by epsilon x plus xp, and your Vx is Qna by 2 epsilon x plus xp whole square. Okay. Similarly, I could do between 0 and xn, right? This is another region, right? So they are, if I write the Gauss law, so this is d by dx equal to, if I do the same thing, this is Qnd by epsilon. And you see, I could find the electric field as a function of x. I have the constant C3. So I could have the boundary condition. The boundary condition is electric field at xn equal to 0, right? So why xn equal to 0? But if you see at this age, right? After this age, I have the neutral region, right? So your electric field has to go to 0, right? So your this is the boundary condition. If I put that boundary condition, I'll get my electric field as a function of x, right? In between 0 and xn, right? So that electric field is Qnd divided by epsilon x minus xn, right? Okay. So then I could put the electric field in the potential term, which is minus dV by dx, right? So then I could write dV by dx equal to minus Qnd by epsilon x minus xn. Again, I'll take the integral. So your potential with x is nothing but minus Qnd by epsilon x square by 2 minus x times xn plus C4, right? C4 is another constant. So now, then I have to put another boundary condition, but keep in mind the voltage. So if you go here, right, go back, right. So the voltage at this point at the left end of the depletion region is 0 because there is no voltage drop. So I am not applying any added external potential. There is no drop in the there is no drop in the neutral region. So the voltage at this point is 0. Potential at this point is 0. But the potential at the end of the depletion region will be the VBI because we discussed yesterday. So there is an electric field in the depletion region, and there is a potential drop, right? And that potential drop is the built-in potential, right? So the built-in potential drop is nothing but the voltage drop in the neutral region. The voltage drop across the depletion region is your built-in potential, right? And and so I have to if I put this boundary condition here, right? So voltage at xn, the potential at xn is VBI, right? So VBI is the built-in potential, and I know, right? So VBI I have derived yesterday, KT by, in the last class, KT by Q ln na nd by ni square, right? Right. So your built-in potential will depend on the doping of both the regions, right? Okay. So then you could solve that using that boundary condition, and finally you'll get your Vx is nothing but minus Qnd divided by 2 epsilon x minus xn whole square plus Vbi, right? So this is the equations. Um, this is the equations for Ax between 0 and xn, right? Okay. So now, if I take these equations here and try to put it, right, so the plot it, right, so so basically, so your electric field in this point is 0 because this is neutral region. So I'm going from left to right, right? Then I have a negative electric field because I'm going from left to right, but the electric field direction is from right to left, right? So the field will be negative, right? Okay, right? Then then if I, so basically then so this is my edge of the junction. This is my junction region here. Then after it crosses the junction, your charge changes from negative to positive, right? So the field will change, right? So so the field will not change, so the magnitude will reduce, right? Right. So this is between 0 to xn, and again in the neutral region it will go to 0, right? This is how the field, and this is linear, right? So your field is linearly increasing and then linearly decreasing. So this is linearly increasing till the junction, then again it is linearly decreasing till the depletion is, right? And if you plot the potential, so potential is 0, right? Then it is a quadratic, right? And there is a potential drop of VBI, right? So this is how your potential will look like, right? So your energy, if you plot energy, energy is nothing but minus q times Vx. So you'll see your energy means, let me plot that. So so your energy, right? So okay, so you could so basically if you plot your energy is minus q times Vx, so you just multiply minus q, so you will have uh, energy will also be like this, right? Oh, sorry. Yeah, right. It should be like this, right? Because this will just replicate the, right? And this can be EC or EV, whatever you plot, right? And this is nothing but minus q times your Vx, right? Okay. Uh, so and basically, so this is p side and n side. If you draw the band diagram, your band diagram will exactly look like this, right? So your band diagram will also look like this, right? So you could plot EC, then you could plot EV also. So your band diagram uh, will also look like this, right? Okay. So yeah, so I have gone through it quickly, but means you know this derivation, so I don't have to spend much time here. Uh, so only thing that I have to take from this derivation is your electric field is maximum at the junction, right? Um, and your potential change is quadratic, right? So let's say here you have given a homojunction, right? Homojunction means your p type is in silicon and n type is silicon, but if you have uh, p type is germanium and n type is gallium arsenide or some other semiconductor material, then you have to be very careful while solving, uh, right? Because when you take the epsilon here, the epsilon cannot be same, right? And there might be a discontinuity in the band gap, right? So you have to learn how to solve this for a heterogeneous semiconductor, right? Heterogeneous junction. All right. Any questions here?
Sir, the voltage, the outer surface of the p type is equals to the voltage at the outer side of the n side, right?
No. Yeah. No, yeah. This okay. I got your point. What you're asking. So I'm not applying any voltage here. So this is zero. This is zero, right? So basically, if you means let's say you have a PN junction, and if you take a multimeter measure the voltage difference between two terminals, it is always zero if you're not applying voltage, right? But the point is across the junction, right? There is a voltage drop, right? And that voltage drop is VBI, right? So so basically VBI you cannot really measure by the potential, because as I told you, right? So means in if you're let's say these are two metals, if you're not applying any voltages and these two metals are same, then their formula level of these two metals will not show any difference, right? So there will be no voltage, we couldn't really measure any voltage difference, right? So Bhavesh, your question is, if there is a voltage difference VVI, then the terminal between these two terminals there will be a voltage difference of VVI. What is the question?
Yes, sir. This graphically it is showing that the voltage is VBI.
Yeah,
But
this VBI means basically this is okay. You could think of this built-in potential is the voltage drop across the junction, right? But you cannot really measure it. You cannot really see it outside, right? Outside, what are you measuring is the voltage difference. Let's say I have a metal here and I have another metal here, right? If these metals both are grounded and their Fermi levels will be same, right? So you cannot really measure the voltage difference, right, from the external, right? But if somehow you could point out, I mean, the if you could measure the voltage between two junction, but this is very difficult to measure. You cannot really measure. So the voltage drop across the junction is the built-in potential.
Okay, sir.
Sir, as VB, the Vx was increasing as we grow from P side to N side in the junction. So shouldn't the graph be upside down of Vx?
Oh, yeah, yeah. So that is fine. See, okay, I got your point. Ohm. So means I have just plotted it. So the point is, see, it doesn't really matter, right? So this electric, so whether the, okay, if you see the electric field plot, right? Whether this is like this or this is like this is almost same. Only thing the electric field is direction is different, right? So and also from potential point of view, you are right? So actually, your potential will increase because your field is reducing. So you could have a positive voltage drop between P and N, but that is immaterial because you always talk about the magnitude of the voltage drop, right? Voltage drop, right? So voltage drop across the junction is VBI, right? Whether that is negative or positive, it really doesn't matter, right?
Yes, sir.
Okay, so so I can do some little bit more derivation, means more mathematics here. So this is my the electric field and the potential between minus xp and 0, and this is my electric field and potential between 0 and xn, right? uh, and if I find at the junction uh, the voltage at the junction v equal to 0 from both these equations, because your voltage is continuous, right? So v equal to 0 is qna by 2 epsilon xp square from the first uh, uh, from here, and from here it will be like this, and both the voltages are same, right? So you could equate it. So basically from here you could find your vbi, your built-in potential, is nothing but q by 2 epsilon na xp square plus nd xn square. So you could do little bit more math. We know that NAXP equal to ND times XN. So if you do this math, right, and you load it little bit more, so you'll find that your built-in potential VBI will be Q by 2 epsilon ND square XN square divided 1 plus 1 by NA plus 1 by ND, right? From here, you could find the depletion width in the N side and depletion width in the P side. So your depletion width in the N side, you could write it like this, right? And or in the simpler form. So this is 2 epsilon VBI times Na divided Q ND Na plus ND whole root over, right? Similarly, XP you could write it by this formula here, right? And total depletion width is this one, right? So the xn plus xp, right? But here you see it is if you look at this equation here xn, so you know na, um, you know na, you know nd also, you know vbi, because vbi is kt by q ln nd nd by n square, na nd by ni square. So you could find this xn, right? You could find xn, and similarly you could find xp. You could also find the depletion width, right? If you know xn and xp, you add this, right? So these are the very simpler equations. So but the assumption here is your doping in p side and n side is constant, right? Which is not the case always, right? We'll see that p side, the your doping is not always constant. So there is always a decrease, because in the implantation you cannot have a uniform doping, right? So but here we have assumed that the doping is uniform, right? So p side doping is constant with x, and n side doping is constant, right? But if you take gradient doping also, so it will not be much change, right? You could still find xp and xn and wd from this simple simple formula. again, so if you see, let me take this, the total depletion width, right? So let's say your if ND is much higher than Na, so these are the cases we call them abrupt junctions, right? Abrupt junctions are very common in semiconductor devices, right? So for example, in your NMOS or in your MOS transistor, you have N plus region here and P region here, and if you look at this junction, right, if you look at these junctions here, so they are abrupt, right? Why abrupt? Because uh, your N doping is much higher than P doping, right? So N doping is around 10 to the power 21 here, and P doping in the MOS transistor is around 10 to 17. So your ND is much higher than Na. So if I look at the WD in this case, right, so I could simplify it, right? So I could simplify, if ND is much higher than Na, then I could write my Na plus ND is ND, and you'll see you could just by 1 by Na, right? So you could put that inside. So I could put that inside here, and I could write QNA, right? So your depletion width for abrupt junction is determined by the lowest doping part, right? So in case of MOS transistor, right, so your source and drain are N plus, right, but the depletion width is not dependent on the doping of source and drain. It depends on the doping of substrate, right? And so all the properties of the junction, right, all the properties of junction is now controlled by the doping of p type substrate, right? Because if you want to find the electric field, right, so electric field right, so electric field will also depend. So okay, what will be the electric field, what will be the potential drop? The potential drop uh, uh, across this junction is nothing but the potential drop in the NP side, right? Because you will not have any N side depletion region in this case, right? And your electric field across this junction will determined by the doping of P side, right? So in abrupt junctions, and which we'll encounter a lot in our in our transistors, so the properties of the junction will depend on the lowest doped side, right? So the breakdown voltage of the junction, the potential drop across the junction, everything will depend on the on the lowest doped side. So by managing the doping of the lowest doped side, you could increase or decrease the breakdown voltage of the junction, right? So why this breakdown voltage of the junction is very important? Because if you take example of your MOS transistor, you apply VDD to to drain, right? And your substrate is also grounded. We'll discuss what MOS transistor later, right? So you apply VDD and your substrate is grounded. So these junctions should withstand VDD voltage, right? Otherwise, there will be a breakdown, right? So how do you design that junction so that it withstand your VDD? You don't have to do anything with N plus, right? So what you have to do is you have to manage the doping of P region, right? By changing the doping of the P region, you could have the breakdown voltage of junction more than VDD, so that it could withstand your VDD voltage, right? Okay. So these are the abrupt junctions, and abrupt junctions we'll mostly deal with abrupt junctions, right? Okay. So um, uh, okay, so I think this part is clear. You do not have more questions. Anybody has any questions here? Okay, so if not, so let's go to our next part. What will happen if you apply voltage, right? So now we are discussing that our junction is neutral, right? My junction is neutral. That means I'm not applying any voltage, right? Let's say this is N side um, let's say this is your p side and this is n side, and this is your minus xp and this is your xn. So what I've done now is I forward bias this junction. So forward bias means I anyway, so n is at ground and we apply some voltage here, right? Let's say this is your applied voltage, right? So okay, so what will happen here, right? So the point is, if you draw the band diagram, um, uh, in the neutral region, I mean, you could draw the band diagram P and N. So let me draw quickly. So this is my formulable, and this is P side. So I have to draw the I have to draw I could draw the valence band and conduction band, and this is my N side. So I have to draw conduction band and valence band, right? And I could draw the and I means I know here. So okay, so my junction is somewhere here, right? And I could connect, right? So I could connect it, right? Okay, so this is in the neutral. So in the equilibrium condition, and this is my EF, then EC, then EB, right? So the moment I apply the voltage, so there will be change because uh, so okay, so basically what will happen is, okay, so you forward bias, it will be easier if you do it like that, right? Let's not apply any voltage here, right? Let's apply a minus V applied here, right? So so this is forward bias condition, right? Okay, so let me see, right? So right, so this is my neutral, I mean, this is my band diagram in the equilibrium condition. So as I told you earlier, so I have my states here because this is my region. I have my states here, and also I have my states here, right? Right. So the electrons in the n type at the bottom of the conduction band, and they could not easily go, right? So it is very difficult for the electrons to jump from here to here, right? Because they could not be injected because there is a barrier potential, right? But the electron from here, right, which is uh, from the state which is in par with the conduction band. So let's say this is my ECP, and this is P side conduction band and M side valence, P side valence band, and this is ECN, ECN, and EVN, right? Right. So this state which is at same energy level as ECP, so the electron from here could easily go to the P side, right? Because they are the same energy level, there are no barrier that could go, right? But what is the probability of finding an electron at this point, right? How do you find, what is the probability of finding an electron here?
Almost zero.
Yeah, I mean, don't tell zero. So so this is not, so I know that n equal to nc e to the minus is ec minus ef by kt, right? Right. So n at ECP, then let's say this is at ECP here, right? So n at ECP will be, you could also write down this, right? ECP minus EF by KT, right? Okay. So so basically, if you so if we have uh, electrons here at the bottom of the conduction band, And we also discussed that the concentration of electron will reduce exponentially. And so you could see that I could also write this as, means we have done this exercise earlier. So I could also write them as minus EC minus ECP or ECP I could write as ECN, right? Can I write this as ECN plus Q times VBI? Can I write this? Because this drop here is nothing but Q times VBI, right? So in the, right? So I could write this ECP because there is a voltage, means for a voltage drop of built-in potential across the junction. So ECP and ECN, so there will be energy difference of Q times VBI. So I could write ECP is nothing but ECN plus Q times VBI minus EF by KT, right? Okay. So let me copy this side. I think that will be my last point to make today. Okay. Now I could write this as ENCE minus ECN minus EF by KT times e to the power minus Q VBI by KT, right? And this is nothing but, this part is nothing but N at EC N, right? Times e to the power minus Q VBI by KT, right? So what is telling me is N at ECP is nothing but N at ECN e to the minus Q VBI by KT, right? So somebody was mentioning, I think it was Bhavesh, ki N at ECP will be 0. It will not be 0, right? At N at ECN is nothing but ND, right? So ND is the doping, then it will just exponentially decrease, right? Right, exponential decrease. It might be 0, right? If VBI is let's say 3 times KT by Q, then ND into e to the minus 3, right? If it is 5 times KT by Q VBI, then it will be ND times e to the minus 5, right? Right. So so ECP equal to ND. So what is the significance of this equation? If I think little bit more, so there is the possibility this much electron could be injected, right? So if you see, this is the electron concentration on ECP, right? Only this much electron could be injected, right, to the P side, right? So now, if I give a forward bias, right? So this is at 0. This is the equilibrium condition. Let's say I'll put it 0, right? If I give a forward bias, right? So there will be, so this part will be your potential drop across the junction will be VBI minus V up, right? And this will be ND times U minus Q VBI by KT times e to the power Q V up by KT, right? So what is telling you, right? If I copy this part, here, okay, so N ECP is N0 ECP times e to the power Q V up by KT. So you see, so N0 ECP and the equilibrium, this much electron could be injected, right? But the moment you applied voltage, some V up here, the forward bias it, right? So the number of electrons that could be injected have increased exponentially, right? So the moment you apply forward bias, the number of electrons that could be injected from N to P has increased exponentially, right? So NSCP is the electrons, inject electrons. If you could see, NECP is the electrons at the edge of the depletion region, because this much electron has been injected, because means electrons could easily inject from ECP to this side, and since your so you could write in the non-equilibrium condition, the moment you apply applied voltage, right, the electrons that could be injected has increased by exponential of this voltage, right? So if you want to, in the equilibrium, I have N0 ECP. Now in the moment I apply voltage, I have more injection. So the difference, this is my excess carriers, right? Right. So, right. So this is my excess carrier. Excess carriers will be N0 ECP, right? E to the power Q V applied voltage by KT minus 1, right? So this is called the excess carriers, right? So I had N0. So basically in the equilibrium condition, I have uh, some electrons here, right? I have some electrons on the p side. The moment I apply forward bias, so I inject some part, and the excess carriers is nothing but N0 ECP, e to the Q VR by KT. And N0 ECP is nothing but the equilibrium carrier concentration. This is nothing but, I could write down this as Ni square by Na, right? E Q VR by KT minus 1, right? So this is my excess carriers, right? So the moment you apply some forward bias, right, the electrons, more number of electrons can be injected to the p side, and and the electrons that could be injected to the p side minus the electrons that was already existing in the p side, that is my excess carriers, right? So that is nothing but e to the electrons that are existing in the p side to the power, means into e to the q vr by kt minus 1, right? And this equation is very means this is your diode equation, right? So this e to the q vr by kt is coming here, and this is what your diode equation, right? So basically this term will be there all the time, right? And this is nothing, so this term just tells you that moment you forward bias, these are the excess carriers, and that those excess carriers, once they are injected, right, to the p side here, right, at this edge, and they will diffuse, right, because there is a concentration gradient, right? So I had some equilibrium concentration here in the p side. Now I have injected more number of electrons from n to p, and there is a excess carriers delta n, and this delta n will diffuse because there is a concentration gradient. So this delta n will diffuse and give rise to the current, right? And the current will be diffusion current, because this region is neutral region, right? The p side and n side are neutral region, right? And your current will be the diffusion current. And if you, and we will solve that current equation in the next class, right? I'll stop here because anyway we are 5 minutes above 12. So if you have any questions, you could ask me, because this is a concept which you need to understand. The all this exponential relationship is coming because this exponential relationship will use also in bipolar junction transistor. We'll also use it in the MOS transistor, and this is mainly coming because of your Fermi function, right? This exponential is coming from the Fermi function, and that Fermi function is actually driving all your characteristics of means of the MOS transistors, right?